Oregon and Washington have been identified by the U.S. Geological Survey as very high-threat volcanoes. Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century. Satellites trained on the Pacific Northwest have recently returned images that are impossible to dismiss. The United States Geological Survey responded with a rare and chilling red alert after instruments detected a vast network of magma tunnels apparently threading beneath the Cascades, creating a subterranean link between Mount Rainier, Mount St. Helens, and Mount Hood. Each of these peaks carries its own legacy of eruption and destruction, but together they form a volcanic triad with the potential to reshape the region. For decades, scientists have mapped faults, vents, and chambers under the Cascades. But the sudden recognition that molten rock may be coursing through continuous channels connecting three of the most dangerous volcanoes in North America changes everything about how the landscape is understood. Before we start, smash the like and subscribe buttons for more updates. The Cascades have long been defined as a volatile range, stretching like a scar from Northern California through Oregon and Washington. Within this arc, Mount Rainier looms as the tallest peak, a glacier-laden giant whose slopes are laced with unstable ice fields. Mount St. Helens stands scarred from its 1980 eruption, a blast that stripped forests and altered the skyline in minutes. Mount Hood, nearer to Portland, has its own restless magma beneath. Yet, what no one expected was evidence that these individual systems might not be isolated at all. Satellite-borne sensors detected anomalies, thermal pulses and gravitational disturbances that lined up in patterns too structured to dismiss as random. When mapped, they revealed sinuous paths of molten material, as though rivers of fire had been threading their way beneath the earth for centuries, largely hidden, but now more active than before. The significance of this discovery is staggering. For generations, geologists treated each volcanic mountain as its own entity, driven by its own magma chamber, pressure dynamics, and eruptive history. The idea that Rainier, St. Helens, and Hood might share conduits of molten rock redefines the risks facing the region. If pressure builds in one peak, it may not remain contained. A surge beneath Rainier could translate into an acceleration of activity beneath Hood, or the restless magma under St. Helens might find relief by shifting northward or southward through these tunnels. The interconnectedness means that activity once interpreted as local could actually be part of a larger orchestration underground. The red alert issued by the USGS is not a declaration of eruption, but rather a recognition that the dynamics have shifted into a dangerous phase. Red alerts are rare and reserved for when data crosses thresholds that can no longer be dismissed as background rumbling. In this case, satellites provided a synoptic view of magma motion, capturing not just hotspots, but flow patterns and velocities. Beneath the Cascades, what emerged resembled arteries pumping with renewed vigor. The magma is not dormant. It is restless, creeping through passages like a slow but unstoppable tide. Mount Rainier, with its towering height and heavy glaciation, presents the most immediate hazard if destabilized. Even a moderate eruption could unleash catastrophic lahars, volcanic mudflows that would surge down river valleys, burying towns and threatening communities built in the shadow of the mountain. The discovery of connecting magma tunnels magnifies that danger. Pressure beneath Rainier might not only destabilize its glaciers, but could also transmit force southward. In essence, what happens beneath Rainier may not stay beneath Rainier. Mount St. Helens, though smaller, is a symbol of volcanic destruction. The 1980 eruption proved how violently it can explode, blasting sideways, felling forests, and darkening skies. Since then, its dome has rebuilt in cycles, a visible marker of magma resupply. The detection of subterranean links suggests that its infamous explosiveness may be fueled not only by its own chamber, but also by pulses from beyond. If magma influx from Rainier or Hood adds to its load, the potential for renewed explosive behavior becomes more likely. The mountain that once leveled its surroundings could be recharged by neighbors many miles away. Mount Hood, rising near Portland, has long been considered a sleeping but restless presence. Climbers scale its slopes each year, even as fumaroles hiss near its summit. With the new evidence of magma channels feeding into its base, Hood may no longer be considered the quieter cousin of its northern peaks. Instead, it stands as part of a system that is alive, connected, and increasingly unstable. Portland and its surrounding communities, already aware of Hood's latent risks, must now contend with the idea that their nearby volcano is tied into a triad that could awaken in synchrony. The scientific implications are profound. Volcanology has always grappled with incomplete data. Seismographs reveal tremors. Gas sensors capture emissions, but the subterranean world remains hidden. The satellite revelations peel back that veil, showing that magma does not respect the boundaries humans place on mountains. It moves as it will, guided by faults, density differences, and tectonic stress. The discovery of these tunnels suggests a degree of organization, as though the crust beneath the Cascades has channeled molten rock into pathways that interconnect peaks like organs in a body. This understanding will force a reevaluation of hazard models, as eruptions may not need to originate from local buildup alone, but could be triggered by distant surges. Geopolitically, the alert reverberates as well. The Cascades lie within a densely populated corridor of the Pacific Northwest. Seattle, Tacoma, Olympia, and Portland are all within reach of these giants. Infrastructure, dams, highways, ports, and power grids sprawl across valleys carved by glaciers and rivers descending from these mountains. If magma pressure beneath one peak shifts the balance under another, the region could face simultaneous threats. This interconnectedness complicates emergency planning. No longer can each volcano be addressed in isolation. Instead, a regional strategy must be forged, recognizing that pressure beneath Rainier might signal unrest at Hood or St. Helens. The environmental implications are equally vast. Forests, rivers, and ecosystems surrounding these mountains have already endured centuries of eruptions and regrowth. Should magma movement intensify, the possibility of widespread reshaping of landscapes grows. Ash plumes could smother forests, lahars could reroute rivers, and new vents could tear open previously quiet valleys. Species that rely on delicate alpine ecosystems may face sudden displacement, while salmon-bearing rivers could be choked with debris. The discovery of magma tunnels underscores that these environments are part of a single living system, one that may undergo dramatic changes in ways that ripple across states. On a deeper level, the Red Alert forces reflection on the very nature of the Cascades. The chain exists because of the collision between tectonic plates, where the Juan de Fuca plate dives beneath the North American plate, melting rock that rises as volcanoes. For decades, these mountains have been considered expressions of localized magma pockets. But the tunnels hint at something more integrated. The Cascades might be less a series of independent peaks and more a unified volcanic machine, its arteries stretching across hundreds of miles. This realization alters not only the science, but also the cultural and psychological relationship communities have with their mountains. Residents of the Pacific Northwest often live with a quiet awareness of the volcanoes on their horizon. Rainier is depicted in art and postcards. Hood dominates Portland's skyline, and St. Helens stands as a reminder of nature's force. The Red Alert, however, transforms these familiar landmarks into a network of potential eruption. The psychological weight of knowing that magma threads them together is immense. It suggests that what appears serene and stable may actually be a surface mask for restless movement below. As magma creeps through its hidden channels, the possibility of chain reactions grows. Scientists warn that interconnected systems can behave unpredictably. A pressure release in one area may accelerate buildup elsewhere, while blockages in tunnels could reroute magma suddenly. The tunnels themselves may act like fuse lines, transferring instability across distances. This is why the USGS did not hesitate in raising the alert to red. It is not only the possibility of eruption that is concerning, but the complexity of a network system that defies simple predictions. The role of satellites in uncovering this reality cannot be understated. From orbit, instruments detect subtle shifts in the Earth's surface, heat emissions invisible to the eye, and gravitational anomalies that betray movement underground. It was this vantage point that made it possible to see the broader pattern, connecting the dots that ground-based sensors might have missed. In a sense, the sky revealed what the Earth concealed. The revelation serves as a reminder of how technology expands human perception, allowing scientists to perceive the invisible architecture of magma beneath the Cascades. For the scientific community, the discovery is both alarming and exhilarating. It opens new avenues of research into how volcanic systems interconnect, how pressure transfers, and how eruptions cascade through networks. Models once based on isolated chambers must now incorporate linked systems with feedback loops and shared conduits. This represents a frontier in volcanology, as complex as the study of weather or climate, where interactions multiply and predictions require immense computing power. The Cascades have thus become a laboratory for understanding interconnected volcanism. Their magma tunnels, offering data that could redefine hazard science globally. The Red Alert, while sobering, is also a call to awareness. It compels governments, communities, and individuals to recognize that the familiar peaks are bound together beneath the surface. While no one can say with certainty what will happen next, the discovery of magma tunnels and the heightened activity within them leave no doubt that the Cascades are more alive than previously believed. The mountains breathe through shared veins of molten rock, and satellites have caught them in motion. The implications reach beyond geology. They touch on culture, infrastructure, environment, and psychology. The Pacific Northwest, a region of dense cities, lush forests, and iconic mountains, now faces the reality that its giants are connected in ways that make them both more magnificent and more menacing. The Red Alert is not the end of the story, but the beginning of a new chapter in understanding and living with the Cascades. As magma courses through its hidden arteries, the land waits. The peaks stand watch, and the world looks on, aware that beneath the surface, something immense is stirring. The Red Alert declaration from the USGS did more than send a shudder across scientific circles. It revealed a panorama of hidden geological dynamics that few had considered possible. With the confirmation of magma tunnels linking Mount Rainier, Mount St. Helens, and Mount Hood, the conversation quickly turned to the scale of processes shaping the crust of the Pacific Northwest. These tunnels were not fleeting or temporary structures. They represented enduring geological features forged through pressure, heat, and tectonic stress over millennia. The revelation forces a deeper examination of the mechanics that sustain such conduits and why their significance is only now becoming undeniable. At the heart of these magma tunnels lies the principle of connectivity. For magma to move through solid rock, pathways must exist where fractures, porous zones, or weaknesses in the crust allow molten rock to seep and then surge. Over thousands of years, magma repeatedly intruding into these channels widens them, stabilizing them into semi-permanent arteries of molten material. The new satellite imaging revealed not only the existence of these tunnels, but also their activity, signatures of heat, density anomalies, and subtle uplift on the surface, all confirming movement. The idea that magma flows like an underground river between some of the continent's most dangerous peaks pushes scientific understanding toward a vision of volcanoes as nodes in a massive interlinked network. To imagine this system is to picture a living body where each volcano is an organ and the magma tunnels are veins and arteries carrying fiery lifeblood. Mount Rainier, immense and glacier-capped, acts like a reservoir where magma builds beneath crushing pressure. Mount St. Helens, volatile and explosive, functions like a valve capable of violent release. Mount Hood, slightly more subdued but far from benign, is like a chamber constantly fed with restless energy. Together, they form a cycle of pressure and release, each influencing the others, each shaping the larger system in ways that transcend local geology. This discovery also forces geologists to revisit past events. The infamous eruption of Mount St. Helens in 1980 devastated landscapes and claimed lives. But what if that explosion was not merely the product of localized pressure? Could magma transfers from Rainier or Hood have contributed to its instability? Similarly, smaller eruptions at Mount Hood in the 18th and 19th centuries might not have been isolated flares, but part of a broader cascade of movements through the subterranean network. Historical records, when reinterpreted with this new understanding, may point to synchronization and resonance among these volcanoes, where one eruption subtly primes another. What is particularly arresting is the scale of hazard this interconnectedness presents. The Pacific Northwest is not sparsely populated wilderness. It is home to sprawling urban centers, critical transport corridors, and agricultural heartlands. Highways wind past river valleys that could one day serve as channels for lahars. Power lines, pipelines, and water systems trace routes vulnerable to volcanic upheaval. The magma tunnels effectively mean that an eruption or instability at one volcano is not just a local crisis, but could be the trigger for wider disruption. Authorities tasked with hazard planning must now think not just in terms of one mountain, but of a system of mountains with linked fates. From a technological perspective, the discovery is also a triumph of remote sensing. Satellites equipped with radar, interferometry, and thermal sensors detected movements so slight that they would be imperceptible to ground instruments. These satellites monitored not just heat, but minute bulges and subsidence of the Earth's surface, signals of magma pushing upward or withdrawing. The patterns that emerged were too orderly to ignore, tracing sinuous paths beneath the range that matched fault lines and ancient volcanic fractures. Without the vantage of orbit, these links would remain hidden. This demonstrates that the Earth, vast and ancient, still conceals profound secrets awaiting the right tools to uncover them. The Red Alert has also triggered discussions about what such tunnels reveal about plate tectonics. The Cascades exist because of subduction, the Juan de Fuca plate plunging beneath the North American plate. As the oceanic plate melts, magma rises to form the arc of volcanoes. The discovery of tunnels suggests that once magma forms, it does not always rise vertically. Instead, it can travel horizontally, exploiting structural weaknesses in the crust. This horizontal migration allows distant volcanoes to share magma, creating the interconnected system now exposed. It is a vivid reminder that the crust is not a rigid shell, but a fractured dynamic mosaic through which molten rock carves its way. On a human level, the implications for emergency preparedness are immense. Communities that once focused exclusively on the nearest volcano must now think regionally. A surge beneath Rainier could mean evacuation warnings not only in Washington, but in Oregon. Increased fumarole activity on Hood could signal mounting pressure at St. Helens. The network means that monitoring cannot remain isolated. It must be integrated across states, agencies, and even international borders. Since Canadian provinces also sit on the northern edge of this volatile chain, coordination, communication, and shared data will be essential to respond effectively to a system that transcends political boundaries. The cultural weight of this revelation is equally powerful. For indigenous peoples of the region, the Cascades have always been alive with spirit and story. Legends tell of battles between mountain spirits, of fire flowing beneath the peaks, of connections unseen. To them, the mountains are not separate entities, but part of a living landscape that breathes, rumbles, and transforms. The scientific discovery of magma tunnels can be seen as a modern echo of these ancient understandings where connectivity is central. It adds a dimension of reverence to the scientific awe, acknowledging that what satellites see today resonates with stories told for generations. Economically, the stakes are formidable. The Pacific Northwest's prosperity relies on stable infrastructure, fertile farmlands, and thriving metropolitan centers. An eruption that disrupts air travel, contaminates water supplies, or buries farmland under ash would ripple through industries far beyond the region. The discovery of interconnected magma tunnels increases the unpredictability of such disruptions. Insurers, urban planners, and policymakers must now reckon with risks that span hundreds of miles and involve multiple potential eruption sites. The cost of inaction, or of underestimating the scale of the threat, could be catastrophic. There is also a scientific exhilaration in exploring how these tunnels formed. Were they carved gradually with slow seepage of magma, hollowing passages over eons? Or were they blasted open during colossal eruptions long before human memory, their scars now reused by modern magma flows? These questions invite new research into the geological history of the Cascades, piecing together a narrative of fire and rock that stretches back millions of years. By studying minerals, isotopes, and chemical signatures, geologists can trace where magma originated and how it traveled, adding detail to the story the satellites have revealed. The tunnels also bring to light the delicate balance within Earth's crust. Magma seeks the path of least resistance. When pressure rises, it exploits weaknesses. By linking volcanoes, the system may prevent catastrophic buildup in one chamber, spreading pressure more evenly. Yet this same process means instability can be transferred rapidly, much like an electrical surge traveling through a grid. One tremor could reverberate across miles, destabilizing another peak far from the origin. It is this duality, balancing relief with risk, that makes the system both fascinating and frightening. Beyond the Cascades, the discovery carries implications for volcanology worldwide. Could other volcanic arcs harbor similar networks? The Andes, the Aleutians, and even the Mediterranean's volcanic fields might conceal hidden magma highways that connect peaks once considered independent. The Pacific Northwest, with its dense population and advanced monitoring, may simply be the first place where such connections have been exposed. The discovery thus expands the global understanding of how Earth's fiery interior communicates across distances. For local residents, the Red Alert has also brought a heightened awareness of the fragility of their surroundings. Towns that see Rainier as a backdrop to daily life, or farmers who cultivate soil enriched by ancient eruptions, must now reckon with the knowledge that their lives play out atop a restless system. This awareness does not always manifest as fear. For many, it deepens respect for the land, a recognition that prosperity here has always been intertwined with risk. But it also drives practical conversations about readiness, stockpiling supplies, knowing evacuation routes, and understanding the signals that may precede volcanic unrest. The tunnels themselves, invisible yet powerful, have become a metaphor for hidden forces that shape lives without notice. They are reminders that the Earth is alive beneath our feet, moving, shifting, and preparing changes that humans cannot control. The Red Alert is not just a scientific designation, but a psychological threshold, marking the moment when invisible processes became undeniable realities. Looking forward, the task now is to refine models that incorporate this new data. Scientists are developing simulations where magma moves not in isolated chambers, but through branching conduits linking multiple peaks. These simulations must account for heat transfer, pressure dynamics, chemical mixing, and tectonic stress. The complexity rivals that of climate models, requiring supercomputers to predict how magma might move, where it might emerge, and how peaks might respond in chain reactions. The challenge is daunting, but the stakes demand no less. The discovery also underscores the role of curiosity and persistence in science. For years, odd tremors, unexplained bulges, and chemical anomalies hinted that the volcanoes were not entirely separate. Yet only with the latest technology could the full picture emerge. It is a testament to the patience of scientific inquiry, where small data points accumulate until a breakthrough transforms understanding.